So welcome to cryptography session. Today I am going to give an introduction about algebraic structures of symmetric key cryptography. So if you go for a basic generalized algorithms, there are Euclid's theorem, extended Euclidean theorem. So these algorithms are used for implementing symmetric key cryptography notations. So there are three basic algebraic structures are available under symmetric key cryptography, which are all namely groups, rings, and fields. So these three algebraic structures are a combination of set, and few operations can be done on it. So based upon the operations performed on a particular set, these notations, these structures will be categorized as groups, rings, and fields. So these groups, rings, and fields are the fundamental elements for the basic mathematical model under a group notation. That means asymmetric cryptography notation. So the first we are going to understand the groups concept. So a group is denoted with the letter G. Sometimes it is denoted as G dot. Here dot is an mathematical operation which is performed in a set. So these operations should be a binary operation. So there are basically four binary operations are available: addition, subtraction, multiplication, and division. So a set which contains unique elements in it, and if you do a mathematical operation on a set, then that is called as groups by satisfying the following properties. So if you want to define a set as a graph, a group, it should satisfy the closure property, associative property, identity, and inverse. So if any set with a particular operation is satisfying these four properties, then that algebraic structure is called as group. So let us take an example for it. So group G, it is denoted with two notations. Here Zn is a set of residues, and plus is a binary operation which is performed on that set of residue. So whether is it satisfy abelian group. So if you want to satisfy a group, closure, associative, identity, inverse property should be true. Then sometimes the group is called as abelian group based upon the satisfaction of commutative property. So let us take an example. I am taking n is equal to 5. So G is equal to Z 5 plus. That means for Z5 set, the set of values, we are going to implement addition operation in it. So set of residues Z5 values are 0, 1, 2, 3, 4. So I already give an explanation for the set of residues find out in previous class. So using that we can able to write the set of elements, unique elements for Z5. Then the first property is closure property. The meaning of closure property is if you do an operation between two variables with the binary notation, the resultant answer should also be available in the set of residue. So here we are taking the addition operation. So A plus B equal to C. Then that answer C should also be available in Z5. So let us take an example for A and B. Here I am taking A value is 3, B value is 2. So 3 plus 2 is 5. But 5 is not an element in Z5. So we should do mod operation. So 5 mod 5 is 0. So 0 is an element which is available in Z5. So with this notations, closure property is satisfied. Associative property means A plus B plus C equal to A plus B plus C. So here I am taking an example values as A is equal to 3, B equal to 2, C equal to 1. So you substitute these three values at both LHS and RHS. So we can write the LHS part as 3 plus 2 plus 1. This is equal to 3 plus 2 plus 1. So the answer is 3 plus 3, 6. It is greater than 5. So you do the mod operation at both the LHS and RHS. So the values are equal. So within this, we can able to satisfy the associative property for Z5 plus. And identity, so if you are doing an addition operation, the identity element is 0. Suppose if they ask the multiplication operation, the identity element is 1. So like that, the formula is A plus E equal to E plus A equal to A, where E is an identity element. Here we are taking identity element as 0. So 3 plus 0 equal to 0 plus 3 equal to 3. So in this way, identity property is satisfied. Then the fourth property is inverse property. So inverse means if plus is given, we should do an additive inverse value. For example, if suppose if they give the multiplication operation, we should use the multiplicative inverse of a particular element. So the formula is A plus A inverse equal to E. Here plus means identity element is 0. So the answer should be 0. So the additive inverse of 3 is 2. So 3 plus 2 mod 5 is 0. So in this way, inverse property is also satisfied. So if closer associative, identity and inverse properties are satisfied, then that set is called as group. And the question is it satisfy abelian group? So if you want to satisfy abelian group, including this 4 property, we should satisfy the commutative property. So the commutative property formula is A plus B equal to B plus A. So you do the same value substitution. So the answers of LHS and RHS parts have same. So if a set which satisfy these 5 properties, then that group is called as abelian group. So I'm giving an example exercise problem for you. You do the same operation with multiplication operation. Only difference is for identity, you should take an element as 1. For inverse, you should take the multiplicative inverse of a given number. So you do the same notation for n is equal to 5 for satisfying the abelian group. So this is your homework part. So in this way, a group can be able to satisfy these 5 properties. So if all 5 properties are satisfied, then it is called as abelian group. So a group which has a finite or a countable number of elements, then that group is called as finite group. Otherwise, it will be called as infinite group. Then we can able to find out the order of group. The other definition for order of group is the number of elements which is available in a group. So we can able to calculate it. So this calculation will be discussed in future videos. So here the definition for abelian. A group is abelian which should satisfy 5 properties. In addition with a group of integers, infinite cyclic group can also be generated with an element 1. So it is also possible. So order of group, it is denoted as pi. So this is the pi notation. So pi of 21. 21 is it is not a prime number. So we can able to write it as a factors of 2 prime numbers 3 and 7. So pi of 3 into pi of 7. Here 3 is a prime number. So if n is a prime number, pi of n is equal to n minus 1. That is the formula. So if you take n is equal to prime number, then pi of n is equal to n minus 1. So in this way, pi of 3 value is 2. 7 is also prime number. So n minus 1 means 6. So 2, 6 are 12. So totally 12 elements are available in a particular group Z21. So those 12 elements are written here. So these numbers are always a co-prime of Z21. So these all 12 numbers are relatively prime to Z21. So in this way, we can able to find out the order of group for a given notation. Like that also, we can able to identify order of element. Then the subgroup concept is discussed in next class. Thank you.